Hello, welcome to another module in this massive open online course. In this module, let us look at another digital modulation technique, that is frequency shift key. Okay. So, we will be looking at a new digital modulation scheme which is termed as frequency shift key. This is a digital modulation scheme, as we have already said. And it is based on the signal space concept that we have previously described. Where we have two pulses, correct, which form an orthonormal basis for the signal space. So, let us again consider our two pulses P1 t equals square root of t cosine 2 pi f1 t 0 less than equal to t less than or equal to t, and we also have P2 t equals square root of 2 over t cosine 2 pi f2 t 0 less than equal to t less than equal to t, and we have f1, or basically we have, well, t equals k1 contains k1 cycles, or the way f1 equals over t, and f2 equals k2 over t, or t is basically k1 over f1 and k2 equal over f2. T equals k1 over f1, and this is also equal to k2 over f2. Contains k1 cycles of P1, that is a sinusoid, first sinusoid at frequency f1, and contains k2 cycles of the other sinusoid at frequency f2. And we have also seen that these two pulses are basically, the first thing is that the energy of the pulses is EP equals P1 square dt equals minus infinity to infinity P2 square equals 1, that is both pulses have unit energy. And more importantly, if you look at the inner product, this is equal to 0, which means these are orthogonal pulses. These are orthogonal pulses. So, we have two pulses which are orthogonal to each other, and also the pulses are basically, both of them have unit energy. Alright, these are orthonormal, these form the basis, orthonormal basis of the signal space. Okay. Now, the digital modulation signal is given as xt equals, well, a times p1t, that is, let us look at it this way, that is corresponding to the information symbol 0, this is the information bit, Okay. Zero is mapped to A times P1t, which is equal to xt, okay, and 1, the information symbol 1 is mapped to A times P2t, which is equal to xt. So, other words, if I have to write it clearly, I have xt corresponding to information symbol 0 corresponding to information symbol 1. This is A times P1t, which is A times square root of 2 by t cosine 2 pi f1t, and corresponding to 1, this is A times P2t, which is A times square root by t cosine 2 pi f2t. And now you can see that if you now look at this xt, correct, what you are doing is you are either mapping it to waveform A times square root of 2 over t cosine 2 pi f1t, or you are mapping it for the information bit 1 to the waveform A times square root of 2 over t cosine 2 pi f2t. Now, if you can observe carefully, these two waveforms cosine 2 pi f1t, cosine 2 pi f2t differ in the frequency. That is, you are switching the frequency from f1 to f2 and f2 to f1, correct. So, to indicate a 1, you are transmitting a waveform at frequency f1. To indicate a 0, you are transmitting a waveform at frequency f1. To indicate a 1, you are transmitting a waveform with frequency f1, correct. And therefore, since these two waveforms are obtained from each other by shifting their frequencies, this scheme, this digital modulation scheme, is termed as frequency shift keying. Okay. So, which is an important point. So, you can observe that both waveforms are differ in frequency, that is, one is obtained from the other by shifting in frequency. Hence, this modulation scheme is termed as this is termed as frequency shift keying, or FSK, since the waveforms are basically frequency shifted versions of each other. Further, once again, assuming that 0 and 1 occur with equal probabilities, equals half, we have average energy equals half A square EP plus half A square EP, which is equal to A square EP, and similar to previous, if we want to set, similar to the previous modulation schemes, if you want to set energy per bit is constant, that is you want to set a constant energy per bit EB implies A square EP has to be EB, and we know EP equals 1, which implies A square equals EB, which implies A equals square root of EB. Okay, so that is what we have, and therefore, once again the transmitted waveforms are either A times square root of 2 over t, that is remember we will get 2 square root of EB over t cosine 2 pi f1 t, or this correspond to 0, correspond to 1, 2 square root of cosine 2 pi f2 t corresponding to 0. Okay. So, now therefore, now consider what happens at the receiver. At the receiver in the digital communication system, once again we have Yt equals Xt plus Nt, where Nt is additive white Gaussian noise. This is your standard, which we have seen so many times so far. This is your additive white Gaussian noise with PSD or with autocorrelation eta naught n naught by 2 delta tau. This is the autocorrelation. Okay. Now, corresponding to the transmission of 0, you have, remember there are two pulses. Okay. A times P1 t is corresponding to the transmission of 0, A times P2 t is corresponds to the transmission of the information bit 1. Therefore, corresponding to the transmission of 0, you will have the addition of noise A times P1 t plus Nt, corresponding to transmission of 1, you will have the addition of noise A times P2 t plus Nt. Okay. So, let us note that. So, corresponding to the transmission of 0, we have Yt equals A times P1 t plus N2 t Nt, corresponding to the transmission of Y of 1 or bit 1, we have A times P2 t plus Nt. Now, we have an interesting conundrum or an interesting puzzle over here. We have two pulses. P1t and P2t. Now, what we need to determine is when we matched filter, if we want to use, and we have not seen a situation like this before, if you use a matched filter, is Ht equals P1 t minus tau, or is it equal to, surprisingly, is it equal to P2 t minus. So, which one should we choose? So, which pulse should be chosen for matched filtering? That is the basic question that we are trying to address. So, which pulse should be chosen for matched filtering, and it is not immediately obvious which pulse should be chosen for matched filtering. So, let us try to address in a different way. Okay. So, let us, what we will do is we will try to modify this received signal Yt a little and try to see if we can derive from it what the optimal matched filter should be. Okay. So, for that what I am going to do is from y t I am going to subtract a times p 1 t plus p 2 t divided by 2. Now, this is a constant signal. So, I can always do it constant signal, and let us denote this as, let us denote this by y tilde t. Now, therefore, corresponding to the transmission of 0, for 0 we have, or for information bit 0 we have y t equals a times p 1 t plus n t, y tilde t equals y t minus a times p 1 t plus p 2 t divided by 2, which is equal to, well, a times p 1 t minus a times p 1 t, a times p 1 t plus n t minus a times p 1 t plus p 2 t divided by 2. This is equal to a times p 1 t minus p 2 t divided by 2 plus n t. Similarly, so let us call this as p tilde t, that is your p 1 t minus p 2 t divided by 2 is p tilde t. So, that is a times p tilde t plus n t, and further for 1 or for information bit 1, we have y t equals a times p 2 t plus n t, and y tilde t equals y t minus a times p 1 t plus p 2 t divided by 2, which is equal to, well, it has p 2 t plus n t minus a times p 1 t plus p 2 t divided by 2. This is equal to a times p 2 t minus p 1 t divided by 2 plus n t. And now, if you see, this is p 2 minus p 1 t divided by 2, which is minus p tilde. So, this is minus a p tilde t plus n t. And now, you have something very interesting. If you look at y tilde t, not y t, but y tilde t, this reduces to a times p tilde t plus n t, and in the other scenario this is minus a times p tilde t plus n t. And if you look at this, this is similar to binary phase shift key, that is a times, in binary phase shift keying we have a times p t and minus a times p t. Here we have a times p tilde t and minus a times p tilde t. Okay, the only difference is we are replacing p by p tilde, okay, in comparison to binary phase shift key. Therefore, you can see that the optimal matched filter will be p tilde t, not p 1 t or p 2 t, but p tilde t, and p tilde t is nothing but p 1 t minus p 2 t divided by 2. The 2 is simply a scaling factor. So, basically the optimal matched filter will be proportional to p 1 t minus p 2 t, neither p 1 t nor p 2 t, but basically p 1 t minus p 2 t. That is the important point that one has to realize. Okay. So, this is similar. So, note that this is similar to binary phase shift key. and is obtained by replacing Pt by P tilde t. P tilde t is basically your P1 t minus P2 t divided by 2. Therefore, optimal matched filter Therefore, the optimal matched filter is Ht equals P tilde t minus tau, that is matched to P tilde t. P tilde t equals P1 t minus P2 t divided by 2. Finally, note that this 2, this factor of half, is simply a scaling factor, it does not affect the SINR. Hence, which does not affect the SINR. Hence, optimal matched filter is simply, you can say, Ht equals, well, P1 t minus tau minus, this is your optimal matched filter, or basically, which is basically square root of, well, you can square root of 2 over t cosine 2 pi f1 t minus square root of 2 over t cosine 2 pi f2 t. This is the optimal, this is the optimal, or this is the matched filter, this is the optimal filter which maximizes the SNR. Optimal filter at the SNR, which optimal filter at the receiver, which maximizes the SNR. Okay, so that is basically proportional to P1 t minus P2 t. One can simply choose P1 t minus P2. One can choose P1 t minus P2 t, that is P1 t minus P2 t divided by 2, or basically simply P1 t minus P2 t. Therefore, the optimal matched filter will be P1 capital T minus tau and minus P2 capital T minus tau. Okay, so that is basically your matched filter. Okay, I am sorry, I have to simply change this. This is not T, but rather T minus tau. Similarly, over here, the optimum matched filter is F2 T minus tau. So, this is P1 T minus tau minus P2 T. So, it is matched to P1 T minus P2 T, which is P1 T minus tau minus P2 T minus tau. That is the optimal matched filter. Okay. So, employing the matched filter, one can again carry out the analysis at the receiver. So, employing this matched filter that we have derived, correct. Employing this matched filter, one can again carry out the analysis, the rest of the analysis at the receiver, okay, derive what is the signal to noise power ratio and also what is the corresponding probability of bit error, which we will do in the subsequent module. Thank you very much.